I've also learned something today. Okay, so here we go again. That's going to go off the video again. All right. So here we go again, second part of today's lecture. And we're moving on to two-dimensional convolutions and their extensions. Okay, so we've already seen motivation even with sound for two-dimensional convolutions because of this guy. Okay, because we wanted some special thing that would happen here, right, in this two-dimensional convolution that would work on all channels. But by default, it's something we want with images. All right. So here's a rough definition of a two-dimensional convolution of an image X. Okay, so X is now an image. Okay, and it's not a color image; it's an image. It's a monochrome image. Okay, so X is an image. All right, an M by N image with entries Xij, and a filter H. Okay, and a filter H. Okay, and H, the filter is typically going to be much smaller. H might be 3 by 3, or maybe it'll be 5 by 5, maybe it'll be 7 by 7, maybe 17 by 17. It's typically going to be odd because there's going to be, like when you have a 3 by 3 filter, say, that filter focuses on some center pixel. So odd numbers have a center pixel. Okay, so what we're going to do is we're going to, for the ijth entry of the output, we're going to run over all of the entries of the filter, U1 to L, and L is, again, L maybe is 3 in this case, or 5, etc., not too big, of the entries of the filter, and we're going to take the image in some location. And the indices of the image, we've put this to be quite general here. The first index is I, U, and the second index is BJS. So that index depends on the I and the J of where we are, and on the U and the S. Okay, and we're writing it like this because now convolutions, image convolutions, come in different flavors, and they're going to be all these parameters, and they basically affect these integer functions A and B. And it's not so, to actually write how they affect mathematically is not so important once we understand. You need to write it if you're actually coding something in a convolutional implementation of a deep neural network. But we're actually you're not gonna implement a convolutional deep neural network from first principles. There's not a whole lot of reason to do that. Okay, now just to view it more generally, and this is how you'd see it if you'd see it kind of viewed elsewhere. So let's say that's your input image X, okay? And I'll try to be somehow precise here. So X has quite a lot of pixels, okay? In the order of hundreds or dozens, okay? That's your X. And what you're gonna do, and this is your filter, H, okay? H is just, say, 3 by 3, so I'm just drawing it like this. That's your H, okay? And what you're gonna do is you're gonna take this guy and you're gonna multiply, you're gonna do now the inner product of the red guy and what's underneath, and that's going to give you the first output image. Okay, that's going to be this first entry which you get here. Okay, let me undo a bit so I can actually move this guy more. Okay, and then you're going to shift 1 to the right, or maybe 2 to the right, depending. We'll see that in a second. And that's going to be the second entry. And every time you're going to do the inner product. Now, when I say inner product, you guys know what an inner product of two vectors is, right? It's, I mean, the standard kind of Euclidean inner product or the standard inner product, is just this, add up the entries of a vector. When we're speaking about matrices, because this H is a matrix and this X is a matrix, or this subset of X is a matrix, you just add every corresponding entry. It's very simple. And the same will be for volumes. Okay, so that's how you do two-dimensional convolutions. And again, here there's a story about, there is a proper two-dimensional convolution which does flipping, and then it kind of maintains commutativity, but it's not important in convolutional neural networks. Okay, so this video, let's just see, going to the, I recommend, if you haven't watched watch this video, it does more than just showing a two-dimensional convolution. It actually shows how it kind of operates in a convolutional neural network. Okay, but let me use now this chance to actually deviate from convolutional neural networks and just do a very basic image convolution. Okay, a very basic image convolution. And again, the world of oh, you can see, you can see now this horse. Sorry, now when I change computer, yes, my chat disappears. Yes, you can see a horse. Good. The horse cannot see you. All right. So what I'm showing you now is relevant in the context of this video, which I do recommend you watch, but it's not mandatory or critical. It's kind of long, but it's by the incredible Grant Sanderson. This video, which speaks all about convolutions. Okay, it uses Julia, but that's not the key point here. Okay, so convolutions not in the context necessarily of convolutional neural networks, but to understand why convolutional neural network works, you might want to understand what we're doing now. Okay, so we're going to do this. We've got this image. It's a horse. We loaded the horse, and what we did here is just some linear combinations of the R, G, and B. These are standard coefficients which make a nice monochrome image from an RGB. Okay, and that's a plot of the horse. So now this is going to be our 3x3 convolution kernel. The word kernel. Okay, kernel is the filter. Kernel is synonymous with filter. The convolution kernel is what you're moving. This kernel, by the way, is not this kernel. This kernel is a kernel that runs the software. That's a different kernel. Okay, you knew that. All right, so this convolution kernel is designed. This is a pre-designed one. That's not one which we're going to learn. Okay, that's a pre-designed one. It's designed to do vertical edge detection. Okay, so look, it has this, what it has is 0 and -1 and +1. And what it's going to do is when you move it across edges, if there isn't a huge change of gradient, then things are going to look pretty much even out because this -1 and this +1 will cancel each other out. But when you're going to go over some vertical edge where you've changed from something being very dark to very light, then you'll get some imbalance. Okay. So just so we see how this thing can work, and don't worry too much about the Julia. The point is we're using, so our image here is this matrix. It's quite a big one. Okay, high resolution image. Okay, so if I take, let's say the 1313, the Julia indexing starts at 1, then this is kind of the top left box of the image. Okay, if I multiply this element wise with H, then what I'm going to do is, this is kind of like putting this H above the image. It's put above this top left and it's being multiplied. Okay, so I'm still going to get something. And if I sum it, then that is the output of the convolution for the top left corner. Okay, now what I want to do is I want to go to all boxes. Like I want to go to 101 to 103 and 211, 213. That's a different 3x3 box. Okay, I want to do it on all. Okay. So to do this, nm is the size of the image. All I'm going to do is I'm just going to scroll this operation for pretty much all of the i's. I'm gonna skip the ones at the end there. Okay, and all of the j's. Okay, I mean this looks sort of like Python and R comprehensions, but don't worry about the language too much. That's a Julia comprehension. Okay, and then I'm going to plot this y. So it's actually computing for a bit. We're doing it very ineffectively here in multiple ways. Okay, I mean we could have done this with an FFT in a faster way. We could have done it in different ways, also just in terms of memory locality, etc. This is taking some time. But what you get is this image. Now, I don't know if you can see, but you might see a bit of edges here. Do you see that there was some edge detection going on, or vertical edge detection? You see the vertical edges of the horse. Just to filter this a bit more, we're just going to throw away, we're going to find the 90th. So there's a lot of noise there. So we're going to throw the 90th, all the entries that are less than the 90th quantile, and just plot the points where of the filter image were beyond the 90th quantile. And what you see is that we got some rough indication of the edges of the horse. Okay, so this was a very bad attempt at doing early stage image processing, but at least you saw, okay, well, this is how some convolution filter, two-dimensional convolution filter, can work and do something. Okay, detect edges in this case. Now, there was a question during the break, hey, are we specifying these things in deep neural networks? And the answer is no, certainly no. Deep neural networks will learn about these things themselves, but also as we go deeper into the network, they'll combine more and more features to do completely different things. Okay, but this should kind of motivate the fact that convolutions have power in image signal processing, and it's not just in image signal processing. Are there any questions? I'll go back to the iPad. Okay, I think we're there. All right. So now let's speak about some details. And these details are important because part of the purpose of you doing this course is to actually speak the language of deep learning so you understand the details. And those details are going to specify how exactly what, converted to kind of mathematics, it's what are these A's and B's that are actually telling us how to move the thing. So there's a few things. There's something called stride, and stride means how many slots do you move at a time. A stride of 1 means that you move 1 at a time, as you did in a standard convolution. But sometimes you do a stride of 2, okay? Maybe a stride of 3. You're not going to do like the stride is not going to be too big so that convolution kernels don't overlap, okay? There's something called padding, which is kind of an edge story. Padding means that you'll pad the image a bit, because for example, in the convolution that I just did for you in code, actually the image became a bit smaller because I didn't have padding, okay, because I didn't reach the end. Okay, and padding is typically you just do 0 padding, and yes, that adds some distortion at the end of the image. No big deal. I mean, big deal, but no big deal. I mean, there's so many other things happening there. Okay, and there's something that's less commonly used that's called dilation, which is actually taking your convolution kernel and kind of making it a bit bigger. But we won't speak about that further. There's just a link here for those that are interested at the bottom. There's a blog post dealing with dilation. Okay, so but that's not a common thing. Okay. But let's focus on stride and padding for a few minutes. And for this, the thing is, we don't need to do this in the context of multidimensional convolutions. It's fine that we actually work in just you go back to the basics that we started with, just a very simple convolution of an input vector x, which is, of course, this manufactured vector 1, 2, 3, 1, 2, 3, 1, 2, 3 of length 9. And let's say that our convolution kernel is this h. Okay, this h, this convolution kernel has a meaning. It's actually when you're doing moving average on a time series and running this, that's what this convolution kernel is doing. Okay, it's a moving average of length 3. Okay, because the output's all the time going to be the average of 3 guys. Of course, this series here is very degenerate. 1, 2, 3, 1, 2, 3, 1, 2, 3. It looks like that. So moving average will be a bit degenerate as well, but that's fine. Okay. All right. So there's quite a lot of detail here, but not so much to worry about. So in the basic sense, let's start with a padding of 2. Okay, so with a padding of 2, what we're going to do is we're going to put 2 here and 2 here. And one can also speak about unsymmetric padding, like more at one side, less at the other, etc. Let's not worry about that. Okay, and then when you're doing the convolution, the first thing that you're doing is you're taking your convolution filter. It's this guy. Okay, and doing the inner product of this thing that I circled in red with this thing that I'm circling and that I'm rounding in blue. Okay, doing the inner product, taking the output, this times that, this times that, this times that, add them, you get a third. Okay, that's how you do it. Okay, and then you shift one to the right, and you again do the inner product, and you get 1, okay, because a third plus 2/3 is 1. And you continue shifting to the right, and that's what you get. And I have here some formatting error. That's due to the software I'm using. It's not on the website, okay, because website formatting is okay. All right. So this was with a padding of 2. Okay, and notice that with padding of 2, when we did when we worked on input signal of length 9 and a convolution kernel of length 3, what we got was 9 plus 3 minus 1. And I don't know how to prove this per se, except just saying play around with it and see that this is what you get. You get 11 entries as output, because when you shift and do these 11 things. All right. Let's go to padding of 0. Okay. With padding of 0, you just start here in this edge and you shift the kernel all the way to the right up to this edge. So you're going to get output's going to go from 1 to 7, and they happen to be all equal to 2. Again, our signal is degenerate. That's not so critical. Okay. And finally, let's go for a padding of 1, but a stride of 2. Okay. Stride of 2 means that we start here, and then we don't shift 1 to the right. We do stride of 2. We shift 2 to the right. So this guy shifted 2 to the right. You see, we've never had it 1 to the right. Okay, so of course you've got a smaller signal. You've only got of length 5. Okay, and what we've done here in 1 dimension, you can also do in 2 dimensions. So, and often the dimensions will be the same. Certainly the same for the filters. Filters are almost always square, but even in many networks, the input image is taken to be square. Okay, so when you play around with these things, you can convince yourself that this formula holds. It might be a name for it, but it's not common. So it might be named after a person, but I looked a bit and didn't find the name of the person. It's good just to have a name of a person to a formula, because then you can name the formula. But I guess the person at this point, his or her name is output size. So what Mr. and Mrs. output size found is that the output size of doing a convolution on an input image of size x, which we perhaps augment a bit, we add some padding, okay? This thing that I put here, the padding, the yellow, the orange, never going to be too big, right? It's going to be like a padding of 1, so we add 2, or a padding of 2, we add 4, or a padding of 3, we add 6. That's pretty much as we get. Minus the size of the convolution kernel. And again, this is typically going to be 3 or 5 or 7, not much more. Okay. All right. And then you divide this thing by S. Okay, by the stride. So if stride is 1, you just divide by 1, and then you add 1. So in the most basic form, this formula, like the kind of the important thing to see is nx minus nh plus 1. Okay, it's basically, this is no padding. This is a formula here for no padding and stride of 1, and default stride, the basic stride of 1. Okay, and the reason, by the way, you do padding is when you go down the layers. If you don't do padding, then your image will shrink. But you might want to shrink it anyway, and we'll speak about that. There are 2 ways to shrink it. One way we've just spoken about, one way to shrink the image significantly. What parameter here can shrink the images as we go down the layers significantly? What parameter can the stride, right? So thank you. So the stride is kind of an inherent built-in way to go from an image of size 100 to size 50 immediately if you get stride 2, okay, for example, or from size 100 to size 33 roughly if you have stride size 3. Okay, and that's a way to downsample the image, because sometimes you want to go and shrink as you go down the network, because then your features are more refined. Okay, and there'll also be another way of shrinking, which is max pooling. We'll get to that in a second. Okay, questions? All right. And this is kind of this dealing with padding and stride and convolution size is kind of the bread and butter of actually manipulating convolutional neural networks. Okay, this is kind of the details. Now, this section, some example 2-dimensional filters. I actually showed you this demonstration of an example filter, but again, I recommend you go to this video although it's tangential to what we're doing, and just enjoy this video. This is from the MIT Computational Thinking course. It features Grant Sanderson and others. All right. Now, beyond 2 dimensions. So we understand now convolutions on images. But actually, the basic object we're going to work with is a volume. Okay, so maybe this is a time for us to draw a proper convolutional neural network. So we drew kind of an improper one, this messy drawing here, okay, with a lot of scratches. And now let's draw one properly and see what it's going to look like. Okay, the point is that we have channels. Okay, so back to the story of channels. So what I'm going to draw is I'm going to draw an input image. This is an input. Okay, this is X. I'll try to be a bit cleaner. Input. And let's speak about the typical case where the input image might be, let's say, 20 by 30 by what's going to be the typical dimension here? 3. RGB. Okay. Now, when you draw this, and you already think that there's, so I'm going to draw now this is like the splice it up. Okay. So you could think of it as 3 planes, 3 matrices. You already have 3 channels. And now we're going to the first layer. Now there's a choice. There's an architectural choice. Just like in fully connected networks, there's a choice how many neurons to put in the first layer. So there's a few choices here. The main choice is what size of convolution filter will I use? So let's say that I'll do a filter here, which is 5 by 5. Okay, the common filter sizes are again 5 by 5 or 3 by 3. It's going to be a 5 by 5 filter. But I'm not going to draw the 5 by 5 filter just like that. I'm going to draw it like that. It's going to be 5 by 5. Maybe I'll delete the 5 here and move it to the other side. It's going to be 5 by 5 by what's going to be the depth of the filter? What's going to be the depth? 3. So what I'm going to do is, and let's put our filters like red. Okay, that's our filter. Okay, that's the H, the filter. Okay. So when the network operates, what it's going to do, let's use this bit of, oops, sorry. Let's use this trick. I'm going to use a trick now. What the network's going to do is it's going to move the filter. It's going to be here, and then it'll move here, then it'll move here, then it'll move here, and it'll move here. It's going to move each time according to the stride. Let's just not worry about stride. So it's going to move with a stride of 1. So it's going to move, it's going to move, it's going to move, 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 move. And that filter, let's move it back to its guy, undo. This is kind of high-tech undoing technology. All right, so what it's going to do is it's going to create this first layer associated with its filter. Now, notice we exploit the depth all the way, always fully. So this 3 here, the filter is always going to be the depth of what's the input. Okay, so the input here was 3, the filter is of depth 3. So you could have thought, this is written in the text, you could have thought that within a volume, let's say we had here just a 2, for example, that you move this filter also kind of up and down and don't use all channels. It's kind of related to a question I was asked during the break, right? And then you would have got like a volume. But no, the way convolutional networks are implemented and seem to work well, at least the discoveries of the past couple of years, empirical discoveries, are that you work with a filter all the way in. So the depth is kind of this third dimension, but it doesn't get the same respect as the other dimensions because it's always used fully. Okay, so this here, what we created was channel 1, and everything here. Let me draw it in a different color. Everything here is hidden layer 1, hidden layer 1. But typically we don't just have one filter; we have multiple filters, and hence multiple channels. So then there's going to be a second filter. and they're always taken to be of the same dimension in the same layer, okay? So you won't do like inhomogeneous dimensions of filters per layer, probably for implementation purposes also, but also this, this is not something that's really needed. In this guy, you're also going to move it. I won't do this whole copy paste thing, but you're going to move it, and you're going to get, guess what? Channel 2. Okay. But if you don't mind, what I'm going to do, I'm going to take channel 2 and I'm going to put it just like here above channel 1. So it's like, whoops, come on. Again, I'm going to take channel 2. I'm not going to draw it where I did. I'll place it here. Okay, because channel 2 is the second channel of channel 1. And then we can have maybe a third filter. And let's just do a fourth filter. Okay. And that means we'll have a fourth channel and a third channel. Okay. So I'm basically not going to use all this thing because the output of the first layer is now like this guy. Okay, it's a volume. What's the depth of this volume? Well, it depends. Now, to know what this volume is, we'll get to some things like that. But let's actually let's assume padding equals 0 and stride equals 1. Okay, so let's use the formula. This one. Okay, padding is 0, stride equals 1. So the output dimension is just nx minus nh plus 1, nx minus nh plus 1. So now you tell me what is the width here and the height here. So what do we have here? So we ran a 5x5 convolution. So nx minus nh plus 1. This is with this. So okay, so no, not exactly 15 by 50. This was 20 and 30. Our image wasn't square. Okay, our image wasn't square. So in this dimension, it's indeed 16. In this dimension, it's 16 because 20 minus 5 plus 1 equals 16. That's in this dimension. Yeah, that's a 16. What's in this dimension? 26. Right. So we've got 16 by 26. And what's the depth? What's the depth of this volume? 4. Perfect. Okay, congratulations. This is the first hidden layer. You've met the first hidden layer. Good. All right. So the parameters at play, the architectural parameters at play are filter size, and then you've got these annoyers, but we're not dealing with them in this instance, in this example, but very important, the number of channels. Okay. And then the story can continue. We won't continue it now, but it can continue. You can, well, let's just continue very briefly, maybe. So then you might want to do 3x3 convolutions. But what's going to be the convolution? 3x3 by, what's going to be the depth of these convolutions that we're going to do? And now we're going to the second, we're going to create the second layer, 4. 3x3x4, because we always go all the way to the depth, okay? And how many are we going to create here on the right? Well, that depends. You'll see an example in a moment. But typically, we'll start with maybe some 8 channels, and then we'll go to 16, and then 30, and then maybe we'll go back down. You'll see several different architectures. Okay, and that's the structure of these convolutional neural networks. The point to keep in mind is that the third dimension, and that's kind of described here. Okay, you can read this text. The full dimension, you always go to the full depth. Okay, so your convolutions mix what's happening in the channels, and that's a lot of the strength of convolutional neural networks. Okay, questions, thoughts? Oh, yes, beautiful question. So I almost forgot and made this like a linear network, which can only fly so far. Yes. So we, of course, apply an activation function. Thank you for the question. So at this point here, yes. So at this point, you've done this and you've added a bias. You've added a bias, and you have one bias per channel. So let's actually do this. We'll do plus B, one bias per filter. Plus, a channel is a filter. Plus B1, plus B2, plus B3, and plus B4. Okay. You just add one bias, the same bias shifts the whole thing homogeneously. Okay. And then you apply the activation function ReLU or TANH or sigmoid or PReLU or Liquet ReLU, or make your own function, but ReLU is quite common. Okay. And then these are after the nonlinearity. Thanks for the question. Very good. Yes. All right. There's a thing called one-by-one convolution, which is a convolution which here for example, let's start. Let me take the input image. I'll draw it for a second, and let's say now it's RGB. Okay, so I'm drawing it like red and green and blue. Okay, so somehow this doesn't look right, but you get the picture. That's like an input image, RGB. Okay, now what you can do, and it's not just for input images, it's typically not, is you can run filters which are one by one. Now it seems silly to do a convolution of one by one just on a matrix, but here it's going to be one by 3. Okay, so a one by one convolution just works on mixing the channels together. Okay, for example, to convert RGB into monochrome, it's like doing an RGB. Okay, it's like doing a one by one filter. So one by one convolutions appear in networks as well. Just so you see, there is point in doing them because they mix the channels. All right, so now we can put the bits together for a CNN. We've pretty much done that. There's just one more component. So convolutional neural networks are like fully connected networks, except that, you know, you don't have all these weights. You've actually induced like a sparsity pattern on the matrices, because those tuplets, and you can get a feel from that for this mathematically, just by the fact that look at these tuplets matrices. This is a one-dimensional case, but the principle carries over. Tuplets matrices are sparse and they're low dimensional in their parameterization. Okay, so that's what you've done, but you really haven't changed anything. So far, a convolutional neural network is exactly like a fully connected network, only with sparse repeated matrices. You can effectively write it like that. You shouldn't from an implementation perspective, because it'll be much less effective. But there is just one more component that's often used. It's not difficult, and this guy is called max spooling. Max spooling. Okay, so max spooling, and some people call it a max spooling layer, but sometimes it's not a layer with learned parameters. Okay, so what did I do? This one down here, sorry. Okay, so with max spooling, what you do is you simply go on say squares of say 2 by 2 max spooling, and you got these 4 pixels, and you'll choose the maximal one. Okay, and then you go to an image which is half the size. So if this was, for example, 32 by 32, you go to 16 by 16, where this pixel is a maximum of this 4. And then, you know, you can do all kinds of things like not full stride, like do some overlapping, etc. But the default is then you just go to the next one, and these 4, their maximum is going to go here, and these 4, their maximum is going to go here, etc. These 4, their maximum is going to go there, etc. That's max pooling. Max pooling is simple. Okay, max pooling is the most naive method of downsampling. And there are some kind of heuristic justifications why it works, and actually it empirically worked as well. Okay, so now you know of 2 ways to make images smaller. Max pooling or downsampling. Now the question, can you do mean pooling? Yeah, in principle, mean pooling it would be effectively the same, because I believe it would, because you just kind of go kind of the other extreme. Your network might learn automatically to flip the things. Of course, what you do in training needs to be what you do in production, but we just use max pooling. Okay, you can do other things. You can do averaging. You can do all kinds of things to sample down. But max pooling has become, in a sense, a standard, and you'll see it appear in networks. Okay, so one of the reasons is, we start with a whole bunch of pixels that mean all kinds of different things, and in this first layer that we create, there's often the network will end up training very basic convolutions, so do edge detections and similar things. It'll just learn this thing automatically, and then you'll have like edges and things here. And then, once you have edges, you might say, okay, well, I can now sample a bit down. I don't need that, so I'll do max pooling. So you shrink everything by half. Shrinking everything by half means you have less neurons down in your pipeline, means that things can train faster. Okay, so it's a leaner parameterization, and max pooling is an effective way of doing that. I'm sure there are empirical studies comparing max pooling versus stride that show which is better, etc. Now, of course, you can questions more on that. Okay, so that's max pooling. We'll see an example. All right. There are other elements which also exist in fully connected networks, and these two are batch normalization. Now, you didn't have time in the previous unit, Unit 4, to finish batch normalization, so we'll speak about that when we meet next time. By the way, next time is not going to be tomorrow. Tomorrow is a holiday called Australia Day. Okay, so it's going to be the day after tomorrow, but we'll kind of fill batch normalization. This is not specific. Batch normalization is not specific to convolutional neural networks. It's for any fully connected networks, and it's in the notes here for Unit 4. But just I think, if I'm not mistaken, Benoit just ran out of time and didn't get to this batch normalization right here. Batch normalization and mini batch. Mini batch is a different thing, but batch normalization. Okay, so batch normalization deals with learned parameters within the network on how to renormalize, and that speeds things up. You actually have a question about that in the homework, not in the context of convolutional neural networks. So after I've said all these words that came out of my mouth, the main point is batch normalization, you can put it after convolutional layers or with convolutional layers, works wonderful. Dropout, which is a form of a regularization technique, but it's not regularization by adding a regularization term. It's regularization by actually training some neurons in process and some not, by doing some randomization. And it's in the form like an implicit form of model selection, in a sense. Okay, you would not do dropout on convolutional layers. Okay, you would not do dropout on convolutional layers. And to kind of get a feel for this, look, in a convolutional layer, we'll count parameters, by the way, soon. Okay, so there aren't so many parameters. This convolution is 5 by 5 by 3. That's in my world, 5 by 5, 25 times 3, 75. 75 parameters. Okay, not so many parameters. I mean, it adds up when you have a lot of layers and a lot of channels, but still not so many. So you don't want to do dropout on these. However, as you'll see in a moment, they're typically in convolutional networks, we put a fully connected layer towards the end of the network, and doing dropout there works well, just like it does for fully connected networks. Okay, so that's it. Questions? Okay, we're making some headway, but we're also soon out of time. But I think we're in good time to deal with what we've called here the typical architecture. Okay, the typical architecture. So the typical architecture of convolutional neural networks, you can do it, notability, give us a page. You did it. Okay, so the typical architecture is as follows. So you get an input image, which is 3 by, with a depth of 3, and you stick it in a convolutional layer. So what I'm going to do now, I'm just going to draw the channels of a convolutional layer, and maybe there's like whatever I drew, 7 of them, 1, 2, 3, 4, 5, 6, 6 of them, okay? So that was the first layer. And then you do another convolutional layer, and maybe I'll draw now smaller channels because, you know, you've done some downsampling, maybe you've done some dropout, etc. Maybe there's like 16 layers, okay? So just to make some numbers, maybe this was like 32 by 32. Let's go 320 by 320. Let's say it's for big images, okay? Sensible images, not big. 320 by 320 is not big, but big enough for neural networks. The good, the pre-trained networks that we deal with typically work with 224 by 224. Okay, so even though you start with a high-res image, you downsample it and then feed it to the network. Okay, but let's say that this was like, after max pooling, etc., 180, 180, or something like that. Okay, and then you go like by 40 by 40. Okay, and this had a depth of 6, and this had, say, a depth of 16, and you continue with a few convolutional layers, but let's say that 2 is enough. And what you do now is you go back to the basics. You put a fully connected layer, FC, fully connected layer. So this fully connected layer now treats all of these information in these channels. If this is 40 by 40 by 16, that's like 4 times 4 is 1660. This should be 2560, I believe. Correct me if I'm wrong, but I believe there's 2560 here. Okay. And it puts 2560 neurons, fully connected layer. Okay. And then maybe, let's say, if you're classifying for 1 on 10 labels, it's doing 10 outputs. Okay, 10. Okay, with a softmax, for example, if you're doing classification. So this paradigm of a convolutional neural networks, where you start with convolutional layers and then you put in the end a layer, or sometimes 2 or 3 that are fully connected, is quite common. Now, the justification for this, and this was input. Okay, this was input. So the justification for this is that you will train here filters that will first learn some rough features and then will learn more specific features. And then you'd want your fully connected layer to ensure that all features can intercommunicate. Okay, so you don't want sparsity anymore. Okay. Yeah. And then you'll go this. There's a question: is a fully connected layer a vector? The neurons of a fully connected layer are, you can treat them as a vector. Yeah. And what you do here is this is not going to be a vector, this is going to be a tensor. So the neurons sit in these channels, but you're going to kind of vectorize them and make them a vector. All right. Okay, so let's see an example. Let's see an example. And for this, now I stuck this in this unpleasant place. Okay, so I'll go here and just show this here, show you the example here. So I wrote some code for the example. This is Julia code with a framework Flux, but it doesn't matter. I mean, think of this as just kind of a description of a network. So there's 2 networks here. There's a network which we call model 1. There's a network which we call model 2. Model 1 in this case is a network that's fully connected. Oh, nice question. There's a question: does fully connected mean fully connected to the previous layer or to the following layer? It means fully connected to the previous layer. That's a nice question, yeah. Because you can actually, after a fully connected layer, have a convolutional layer. Yeah. Okay, there's some answers. Okay, good. All right. So model 1 is just a dense network. Okay, these networks are designed to work on something like MNIST, like 28 by 28 inputs. Okay, so 28 by 28 monochrome is your 28 by 28 is 784. Okay. All right. And model 2, and so this is how you specify stuff in Flux, in PyTorch or Keras or TensorFlow. It's going to be slightly different, but the point is that you start with your network. This is what you see at the top. Okay, you have a dense layer that goes from 784 to 200, say, with an activation function that's ReLU, and then you go from 200 neurons to 100 neurons, and that's 10H. That's a second hidden layer. Just for some variety, and then you go from 100 to 10. Okay. What we want to look at is this model 2. I think for this I can move back here. Okay, so I can draw on it. So this model 2 has 2 convolutional layers. Oh, it's kind of cut, so sorry, I'll go back here. Okay. This model 2 has 2 convolutional layers. Let's see how to make sense of them. Don't worry too much about the syntax. This is Julia Flux specific, but let's understand the concept. So we have 5, 5. What's that 5, 5? What is kind of the most important thing of a convolutional layer? That's the first convolutional layer, 5, 5. The filter size, we're going on 5 by 5 filters. And then we have 1 going to 8. Why do we start with 1 channel in this case? Why do we start with 1 channel? The input, but the input I thought was 3 typically. Why is it 1 in this case? Why is it 1? Because we designed this network to work on black and white images, on monochrome images. So we start with 1 channel, okay? And then we go to 8 channels. We use activation function ReLU. We use a default stride of 1 and a default padding of 0. I just wrote this purposefully here so we see it, but these, you don't have to write these in this specific framework, okay? So then you get a max pooling. Now, some people call things like max pooling a layer, okay? But mathematically, we don't call it a layer. There's no information in max pooling, okay? By the way, in batch, you could have had batch normalization. There is information there. There are trained parameters, but we don't call it a layer, okay? Some people even call the activation function a layer, okay? Because these are the kind of the things that happen. All right, so then you've got max pooling 2 by 2. Then you've got another convolutional layer. Now you see this 8 going to 16. So how many filters are trained in the second convolutional layer? How many filters are trained in the second convolutional layer? How many filters are trained? 16. Perfect, 16. There's 16 filters. Each is 3 by 3. Okay, and let's just think right there. How many parameters are in the second convolutional layer? How many parameters are there? How many parameters? So for this, we need to think. How many parameters are there? Take a second to think on how many parameters are in the second convolutional layer. Okay, so that's all kinds of different numbers, quite the same order. Let's see. So we said 16 filters. What's the size of each filter? What's the size of each filter? How many parameters in a single filter? Is it 9? Oh, but no, but a filter here needs to work on 8 channels. So it's 9 times 8. And 9 times 8 I always found difficult, by the way. Like in the multiplication table, 9 times 8 for me was the harder one. 72, but not for you. Okay, so 72. All right, so each filter is 72, and there's 16 of these. So 72 times 16, that's beyond me. Okay, 72 times 16. There's 1,152 parameters, which was said there by, yep, you said it. Well done. 1,152, but almost. 152 is the number of parameters in the filters. There's one more learned parameter in this layer. Well, one more type of learned parameter, bias. Great. How many biases? How many bias terms? How many bias terms? Not many, 16. So 100, 152 plus 16, 1,168. Okay, 1,000, I'm putting in the chat. 1,168 parameters in this second layer, unless we made a mistake. Okay, jointly, but this is like collective. Okay, the story continues. So when we meet in 2 days, we'll pick up with this, run this, and then we'll look at an industrial strength architecture like VGG19. Okay, the one we used at the start of the class. And what I do recommend is in this time, enjoy these videos. I mean, this guy, I love him, Siraj Raval. Some people think he's a fluke, but no, he's actually very cool. And this whole lecture, you don't have to watch it. It's a full lecture, but it's going to say more than what we will on the 4 most common architectures. Okay. Similarly here, this whole video is kind of an in-depth video on the residual network architecture. And this is another video dealing with how to understand inner layers. But what we're going to spend a bit more time, there'll be a bit more notes on this, is what we can do with convolutional neural networks beyond classification. So, we just spoke about the basic classification task, but computer vision goes way beyond classification. For example, a state-of-the-art algorithm, YOLO, you only look once, looks at an image and immediately tells you where things are and what they are. Okay, so we'll try and spend a bit of time on that. So come prepared also with some questions after you've done a bit more reading. And just finishing off, we do have some very busy days. So you've got another quiz this weekend. Promise, like really, really promise, it will not be as time consuming and very kind of detailed as the previous one, because it'll deal with neural network architectures and like what are sizes and things like that. Okay, but you still need to know what you're speaking about. So you've got another quiz, that's quiz 2, and homework 2 is not far off. Homework 2 is in the middle of next week. And then you need to start thinking about the project, which you should start thinking about already. Whew, that's it. Any questions? Thoughts? No. Plans for Australia Day? The last thing I see is 1168, assignment 2. That's the best thing to do on Australia Day. Okay. Yes, videos are easy to put up because we just put the link. Yeah, good. All right. Well, everybody, enjoy Australia Day. Eat a kangaroo or something like that, and see you in 2 days. Bye-bye.